One of the earliest concepts in thermal physics that causes confusion is the difference between heat and temperature. In our mind, heat and temperature seem to mean the same thing. Physically, this isn't true, though. Heat is a form of energy transferred from hot substances to cold ones. Temperature is a measurement of average kinetic energy of the molecules in a system. You'll soon see these must be different, as there are times when adding heat to a system doesn't likewise increase the temperature. In this lesson, we're going to show how heat affects temperature and phase changes in substances. Phase changes happen when a substance goes from a solid to a liquid to a gas and versa. We'll work through an example problem that deals with heating up substances and learn how to read heating curves. We're going to see how heat and temperature interact by calculating how much heat it takes to take 50 grams of negative 20 degree Fahrenheit ice and turn it into 80 degrees Fahrenheit water. In order to do this, we're going to have to use two different energy formulas, one for specific heat and one for latent heat. The specific heat formula that you can see on your screen tells us how much added heat, represented by Q, it takes to change a substance's temperature. Here, M is mass, delta T is change in temperature, and C is specific heat. The specific heat is the amount of heat it takes to raise a substance's temperature by 1 degree Celsius. While the specific heat formula tells us how much heat it takes to raise a substance's temperature, it does not tell us how much heat it takes to change a substance's phase. For that, we use the latent heat formula, Q equals mL. Latent heat, or L, is the heat required to change a substance's phase per unit mass. There are two different types of latent heat of fusion and latent heat of vaporization. The former deals with the substance's change between solid and liquid, and the latter the change between liquid and gas. Specific and latent heat are unique to each substance. For our example, water has the specific and latent heat values that you can see listed on your screen as we speak. J stands for joules, which are units of energy measurement. In this case, we see Jg, or joules per gram, which refers to units of heat energy dispersed over the mass of an object. We use the specific and latent heat equations together when a substance's raise in temperature brings it from one phase to another. In our example, the total heat added, QTOT, would be how much heat it takes to raise the ice's temperature to the point where it melts, QI, plus how much heat it takes to change the ice to water, QITW, plus how much heat it takes to raise the water's temperature, QW, to 80 degrees Fahrenheit. Before we plug in all the information for our problem, we need to do one more thing. We need to convert our temperature from Fahrenheit to Celsius. In order to do this conversion, we use the following formula. C equals F minus 32 times 5 over 9. For this problem, we need to convert our starting temperature of negative 20 degrees Fahrenheit and our ending temperature of 80 degrees Fahrenheit. C equals negative 20 minus 32 times 5 over 9 equals negative 29 degrees Celsius. C equals 80 minus 32 times 5 over 9 equals 27 degrees Celsius. Now we use all the information we've been given in this section to solve our problem. Q total equals 50 grams times 2.01 joules per gram degrees Celsius times 0 degrees Celsius minus negative 29 degrees Celsius plus 50 grams times 334 joules per gram plus 50 grams times 4.18 joules per gram degrees Celsius times 27 degrees Celsius minus 0 degrees Celsius. Q total equals 2,915 joules plus 16,700 joules plus 5,643 joules. Q total equals 25,258 joules. Finally, let's make a quick note about how our temperature intervals for delta T, or the final temperature minus initial temperature, were chosen. These temperature intervals were chosen because of